The diagram here shows the X-ray diffraction patterns taken from a disordered AuCu3 and ordered AuCu3. Now, if we examine these two patterns, we will find some of the lines are common to both. Say for example, the line here, the 1 1 1, this 2 0 0 and this one 2 2 0, they appear in the diffraction pattern for the ordered AuCu3 also. So, these common lines which appear in the X-ray diffraction pattern for ordered AuCu3 as well as in disordered AuCu3 are known as the fundamental lines, as I have already explained. Now, in addition to these, in the ordered material, the XRD pattern shows many extra lines. Say for example, here it is 1 0 0 S, S stands for superlattice and here F stands for fundamental. So, you see that here it is 1 0 0, then 1 1 0, 2 1 0, 2 1 1 etc., and there are many others which appear in the diffraction pattern of ordered AuCu3 only, but not in that of the disordered AuCu3. So, the extra diffraction lines which appear in the XRD pattern of an ordered material, these extra lines are known as the superlattice lines. Now, looking at this diagram, it immediately becomes quite apparent that the intensities of the superlattice lines are much less than that of the fundamental lines. We can even do an order of magnitude calculation regarding the intensities of the fundamental and the superlattice lines. Say for example, we have already seen that in case of a fundamental line in the XRD pattern of an ordered material, we have F is equal to, say let us take a particular example here. Say for example, if we take a particular case, say CuZn, let us consider a particular case CuZn which can exist in both the ordered and disordered condition. So, if we look at the crystal structure factor F for the fundamental lines, it is equal to F Cu plus F Zn. So, it is equal to F Cu plus F Zn. So, naturally, if we make the square of both sides, intensity of the fundamental lines in ordered CuZn will be square of this. On the other hand, if we look at a superlattice line, then Fs is equal to, we have already seen, FCU minus FZN. So, if we make the square, it will be FCU minus FZN square. Now, these F square values appear in the intensity equation for the diffraction lines, as we have already seen. Therefore, if we want to find out the ratio of the intensity of a superlattice to a fundamental line, this is how we can proceed. Say for example, let us assume that diffraction takes place from ordered CU Zn in a direction very close to the forward direction, in a direction very close to the forward direction, and that is 2 theta is equal to 0, very close to that in the forward direction. Now, we know that for scattering taking place in the forward direction, atomic scattering factor of an element becomes equal to its atomic number. When scattering takes place in the forward direction, atomic scattering factor of the scattering atom F becomes equal to its atomic number Z. So, if we are looking at a diffraction taking place from CU Zn in an ordered condition in a direction very close to the forward direction, we can assume that F copper will be very similar, almost the same as its atomic number, and the atomic number is 29. So, it will be F, the atomic scattering factor is 29 for copper atoms. Similarly, Fzn will be equal to the atomic number for zinc. So, we can write it as 30. Now, we can calculate intensity of a superlattice line, intensity of a superlattice line divided by intensity of a fundamental line equal to Fs square divided by F square, and that is equal to FCU minus FZn square divided by FCU plus FZn square. So, if we put the values for that particular diffraction in a direction very close to the forward direction, we can write this will be equal to 29 minus 30 square divided by 29 plus 30 square, and that becomes equal to something like 0.003. So, it becomes something like 0.0, I am sorry, it will be 0003. So, this ratio is 0.003. So, we see that in this particular case, we have assumed that all the different factors which influence the intensity of a diffraction line excepting f are the same, and that is the reason why we have taken only the crystal structure factor into consideration, and on that basis we find that the superlattice lines, their intensities are much less compared to the fundamental lines in case of the particular material which is CuZn. You see, whenever the material we are examining is made up of atoms which are very close in their atomic number, this kind of a situation will arise, that is, the intensity of the superlattice lines will be much less compared to those of the fundamental lines, and this may create a problem if we use the Debye-Scherrer method. The weak superlattice lines, we may not be able to recognize them from the background. If they are very weak, they will almost merge with the background and those will not be visible. But if the material is made up of two elements having very different Z values, then this problem will not arise. In such cases where ordering takes place in a material made up of elements of very close atomic numbers, then X-ray diffraction may not be the right kind of method for finding out the order disorder transformation. In such cases, neutron diffraction may be a better option. In such cases, neutron diffraction may be a much better option, because scattering factors of two elements very close to each other in the periodic table may have very different scattering factors for neutrons. So, in those cases maybe neutron diffraction will be a better method to use. I shall now concentrate on measuring the degree of order, degree of long range order in a material which is fully ordered, in a material which is completely disordered, and in a material which is partially ordered. Now, we will examine these three cases one after another. we know that the long range order parameter S can be written as the ratio x a minus y a divided by 1 minus y a, where x a is a fraction of the a sites which are actually occupied by a atoms, and y a is the fraction of a atoms in the alloy. Then for the three different situations, we can now find out what should be the value of S. Now, when it is fully ordered, we know that the fraction of A sites which are actually occupied by A atoms is equal to 1, because all the A sites will be occupied by A atoms. So, in this case, as we have seen earlier also, we can write it 1 minus y a divided by 1 minus y a equal to 1. So, the value of the long range order parameter S is equal to 1 in case of a fully ordered material. Now, if the material is completely disordered, then what happens? Again, this is the expression, and here number of A sites occupied by A atoms, the maximum fraction of the maximum fraction x a can be equal to the fraction of A atoms actually present in the material. So, here what happens, this ratio becomes x a becomes the same as y a. So, we can write it is y a minus y a divided by 1 minus y a, it becomes equal to 0. So, we see that if you have a completely disordered material, then the long range order parameter S, its value is 0. Now, let us consider a third situation. Say for example, we have a CuZn material, we have a CuZn material. Naturally, if the total number of atoms is equal to 50 for each type of atoms, I would rather change the statement. Say we take CuZn, say total number of atoms in this material is 100. Out of these 100 atoms, copper atoms are 50 in number, zinc atoms are 50 in number. Now, we know that the 50 copper atoms will lie, the 50 copper atoms, they will occupy the corner sites if the material is completely ordered. But let us consider a case that out of 50 copper atoms, only 40 of them are present in their corner sides, 10 are present in the body centered sides. So, we do not have a completely ordered CuZn in the sense that out of 50 copper atoms, only 40 actually occupy the corner sides of the unit cells. You know, if you are completely ordered, all the 50 would have occupied the corner sides, but it is partially ordered. So, say for example, only 40 out of the 50 are occupying the corner sides. Now, what should be the degree of order in this particular case? Now, in this particular case, we know that X A, the fraction of A atoms actually occupying A sides. So, in this particular case, the out of 50, only 40 are actually occupying the corner sides. So, this becomes, so the fraction of copper atoms which occupy the corner sides is equal to 0.8. And what is the fraction of copper atoms actually present in the material? This is equal to 50 out of 100. So, the material contains 100 atoms, only 50 are copper atoms. So, Y A becomes equal to 0.5. So, in this case, what is the value of S? S is equal to X A minus Y A divided by 1 minus Y A. So, this is equal to 0.8 minus 0.5 divided by 1 minus 0.5. It is equal to 0.3 divided by 0.5. It comes to 0.6. So, we see that the particular case we considered here of a copper zinc alloy, where the total number of atoms is 100. So, copper atoms are 50, zinc atoms are 50, and if it so happens that only 40 out of these copper atoms, they occupy the corner sides. If it are fully ordered, all 50 copper atoms would have occupied corner sides only, but we have a situation where the material is not fully ordered. So, out of 50, only 40 are occupying the corner sides. So, in that case, how do we determine the long range order parameter value? Now, in this particular case, X A, that is a fraction of A sides occupied actually by A atoms, will be 40 by 50. So, that will be, because 50 is the total number of copper atoms, out of them only 40 are occupying the right places. So, that will be equal to 0.8. And what about Y A? What is the fraction of copper atoms actually present in the material? The 50 by 100 equal to 0.5. So, the long range order parameter S is equal to 0.8 minus 0.5 divided by 1 minus 0.5. So, it becomes 0.6. So, in this way, for any material which is partially ordered, we can find out the value of the long range order parameter.